Hello, everybody. My name is Masood Olian. I'm a professor in the School of Engineering at Wentworth University, and I'm here to show you a problem right here related to the topic of mechanics of material and to the uh, concept of normal stress and shear stress. So let me actually remove my picture here. There we go. So you guys don't get distracted. So let's read the problem. So we have a bar made of aluminum AB, which is attached to supports at A by a pin of the diameter of 0.625. So you see this pin here has a diameter of 0.625. And the bar has a thickness of 0.6. So this is the thickness and the width of 1.5 inch. Now there are two restrictions. One restriction set on the strength of the bar itself, and one restriction set on the strength of the pin. So for the bar itself, we are given that the allowable tensile stress, which is the maximum stress that this bar can take, is 22 KSI. That's 22,000 PSI. And for the pin, the strength of the pin is 12 KSI. So the allowable shear stress is 12 KSI. Okay? So now what we want to do is, just want to make this iPad flat. What we want to do is to calculate what is the maximum load that we can apply to this. So basically, we have to look at two situations. If the failure happens in the pin, or if the failure happens in the bar, and then calculate the load in each case and then compare and see which one is the right load, the maximum load that we can apply. So to do that, let me start with the pin. So notice that the pin here, let me get rid of these. If you look at the pin, you notice that the pin actually is in double shear. So you see it's going to be sheared off here or sheared off here, shear load. So the pin is in double shear, therefore P is equal to 2V to the shear load is equal to half of the applied load. And I'll work it out right here for you. So you know that the definition of the shear stress is what? V divided by the area of the shear. So if I replace V by P over 2, right, divided by the area of the shear. Now, area of the shear is just a cross-sectional area of this pin. So this area, that's the area of the shear, where this shear is acting on it, this shear load V. Anyways, so this becomes P divided by 2 times AS, right? Then if we go ahead and rearrange the equation and solve for P, so tau times 2 times AS. Now, tau, remember, tau is given, right? Tau is given to be 12 KSI, and there's no need to, by the way, change the unit. So KSI, remember, is kip per inch square, and 2 times the area. Area of the pin is the area of the square here, of the circle here, which is pi r squared or pi diameter squared over 4, right? So 2 times pi over 4 diameter, which is 0.625. I'm running out of space here, squared. And that's inch squared. So you see inch squared and inch squared cancel, right? So the answer, after you do your calculation, should be 7.363 kip. But if you want it in pound, that's 7,363 pounds. So basically, you need a load of that magnitude to bring the shear stress to what? 12 KSI in the pin. Now, what if the failure happens in the bar? But you have to be careful. There's a catch to this problem, guys. If this bar is going to break, is it going to break here? This is interesting pen. I go to red. If it's going to break here, no, it's not going to break there. It's going to break in the weakest section where that pin is. So let me remove this. So the failure is going to happen here, actually. So based on that, if you, first of all, start with the definition of sigma. Sigma is just simply load over area. Therefore, load is sigma times area. But the area is not just B times T, right? That would be the area here, cross-sectional area here. The area, you have to actually, so sigma, which actually, let me just put the value of it, 22 KSI, right? Again, that's 22 kip per inch squared, right? So what is the area? You got to subtract the 1.5, which is B, from 1.5, the diameter of the pin, right? 0.625, and then multiply it by the thickness, which is 0.6. Okay, so basically what you're doing, if I could show you a better picture, you see this is the 0.6, that's the thickness if you look at this picture, and this is where the hole is. That's the 1.5, right? Basically you're removing this from it. See that? You're removing that. So what you have is basically this area, this area, this area. So that's why we remove this 0.625 from that. Okay, so if you do the math, again, inches squared here with the inches squared from multiplying those two. Cancel, right? So this time we get 11.55 KSI, right? Or 11,550 PSI. And then, of course, what is the maximum load that we can apply? Clearly, the maximum load is going to be the smaller of the two. Because what if you made a mistake and you applied this larger load? If you apply this larger load, the shear stress in the pin is going to be much larger than 12 KSI. So when you have a choice between two loads, right, you have to always go with the smaller one. Okay? Thank you for watching. And I appreciate if you subscribe and like the video. Thank you again. I'll see you soon.